Okay, I will start with models, and in a certain sense this is where first order logic, this is where logic should have initially begun, in the sense that if you look at logic as essentially a description language for rigorous mathematics, then essentially your actual mathematics and the description of mathematics begins essentially with first order logic. So, and therefore, it can be applied to the description of let us say things like axiomatic set theory or number theory and so on. So, in a certain sense today we will be looking at certain notion of models, which is and essentially look upon a mathematical theory as a certain model of a set of formulae, and that is what we want to actually that is what the original purpose of logic as a language of formalization came up with. Yeah, and which historically of course it comes up from what is known as Hilbert's program, which is the most, which actually dominated most of 20th century mathematics, when in 1900 David Hilbert actually outlined what he called in the what has come to be called as Hilbert's program, and that was that essentially there is a lot of mathematics developed over 3000 years, and it is not clear whether lots of new theorems have been proposed, lots of new proofs have come up, and lots of generalizations, especially like in analysis and algebra, and the important question that was bugging Hilbert at that time was that, is all of mathematics somehow internally consistent? And Hilbert's program was designed was essentially a question wanting the mathematicians to address this question of, is all the mathematics that we are developing actually consistent? Because there is a danger that you can prove a lot of theorems if you are internally inconsistent. In fact, you can prove practically anything you want if you are completely inconsistent. So, the overriding question was whether mathematics was internally consistent, and therefore, the overriding question was, as a consequence of that, was to actually axiomatize mathematics in such a way that you could rewrite and reformulate all the branches of mathematics starting from some foundation in a non-circular fashion, and therefore, and then at least establish its consistency in some way. That was one thing. And the second question of Hilbert's program was, if you were to algebraize mathematics, how much of it can actually be done in some mechanical fashion, essentially by a machine? How much of it can actually be automated? What can you prove theorems in some automated fashion? Both the notions of, so both of these questions which formed important parts of Hilbert's program of about 20 questions. Hilbert of course was a great all-rounder kind of mathematician. So, his 20 questions addressed to the World Congress of Mathematicians included problems from other areas, right, like ranging from number theory to algebraic geometry, through analytical and differential geometry, all the way through Hilbert spaces and so on and so forth. And it also included things like Riemann hypothesis and the continuum hypothesis and so on and so forth. It included a lot of stuff, and Hilbert as a mathematician was actually empowered because of his all round contributions to various branches of mathematics, starting from number theory to algebraic geometry to Hilbert spaces and to parts of physics. So, he was peculiarly situated and able to address the question of whether this entire body of knowledge is consistent. Is it possible to give it a consistent formulation so that no inconsistencies can be shown? Firstly, is it consistent? Secondly, can it be reformulated in such a way that no inconsistencies can be shown? And thirdly, the question is how much of it can actually be automatable? I mean, is it possible that if you can automatize, you can automate the if not the stating of theorems, can you automate the proofs of theorems? And so, can the question of proof be automated, since a large amount of proving of an algebraic nature involved essentially symbolic processing, the question of whether it can be mechanically evaluated and proofs, whether proofs can come mechanically, was a question that bothered Hilbert. The result of Hilbert's program and the questions he raised in 1901, 1900 or 1901 World Congress of Mathematicians, was actually that it did guide the development of logic and mathematics essentially through the 20th century. Yeah. So, and it gave rise to these notions like computability. So, one of the most important and landmark results was assuming a notion of mechanical evaluation without actually having any formal model of it, except what was available historically through let us say the works of Babbage and Pascal and Leibniz. Except for that, so there is a famous proof by Kurt Gödel which first showed that first order logic is the Hilbert proof system for first order logic is essentially consistent and complete, and when you apply it to something like number theory, essentially through piano arithmetic, there are propositions which cannot be decided by machine basically, and that there are theorems. So, he linked the notions of consistency, completeness and decidability in such a way that if number theory is consistent, then it is not complete, and by using a technique known as arithmetization, he also showed that if number theory is consistent. So, the consistency and completeness of first order number theory dependent on was dependent on whether the first order logic that was used to describe number theory is itself consistent and complete. So, Gödel proved that first order logic itself, if you looked at it independently of its application, its axioms were consistent and complete, but when you applied it to number theory to get what is known as first order number theory, that is, if it is consistent, then it is not complete. And by a notion of arithmetization of syntax, he essentially showed that it is possible to have theorems in first order number theory which cannot be, which are not decidable by any mechanical means. I mean, so even before the notion of, even before the formalization of exactly what is a mechanical means of computing, Gödel could actually come up with this landmark kind of result, and after that came the notion of formalizing the notion of computing from. So, in the works of Church, basically the lambda calculus and combinatory logic, and after that the Turing machine, after that the proof that all these different model Markov algorithms, after that the proof post machines, the proof later that all these machines, all these models and machines are actually equivalent in their power of mechanical evaluation, and therefore, so you can see that it has actually dominated a large part of logic and computer science, and it dominated mathematics to the extent that the fields like topology and analysis were formulated in an axiomatic fashion after Hilbert's talk essentially. So, the formulations of statistics by Kolmogorov, the formulations of topology by Kuratowski and so on and so forth as axiomatic systems essentially came up in the 20th century, and before that they were essentially disparate pieces of mathematics, and it was not clear how they all fitted together. Yeah. So, the notion of models therefore becomes important. Yeah. So, this is a model essentially will be a theory, a mathematical theory for which you are going to give some axiomatization, for example. Yeah. So, we will look at that, the notion of models, but before that we have to look at basic things like satisfiability. So, the notion of satisfiability is of course very simple. In the case of first order logic, we are looking at a sigma structure and a language of first order logic for the signature sigma, right. So, and then you have the notion of a sigma interpretation, which means you have a valuation for the variables along with the sigma structure, and under that valuation you say that this structure A with the valuation V is, that is an interpretation. This interpretation satisfies a formula phi if and only if the truth value of this formula phi under that valuation V is 1, right. So, phi is said to be satisfiable in A if there is a valuation V which will make it true, and a formula is satisfiable if a sigma formula is satisfiable if there exists a sigma interpretation that satisfies it. So, which means a sigma structure A and a valuation V which satisfies it, and if it is so satisfied, then we will call this sigma structure A along with the valuation. So, we will say that this structure A is a model, more accurately a sigma model, if this formula phi is true for all possible valuations. Okay. So, in that sense phi acts as a property that is true of the entire algebra. It is a statement of truth for, so it is independent of valuation firstly, and you are saying that, so therefore, this is this entire algebra is a model of this particular statement phi, right. So, we can of course, instead of having a single statement phi, we could have a set of statements capital phi, and we say A is a model of capital phi, and we denote it by this if and only if it is a model of every formula in capital phi. So, by the way, we will just assume that this capital phi is a non-empty set, and then we can call this phi to be an axiom system for all models of phi. So, you can think of capital phi as the set of all axioms which define all those models for which all the formulae in phi are true, independent of valuations of variables. So, that is so the notion of a model is then, so is then identified with the notion of an axiomatic system. So, what you are essentially saying therefore is that if I can find some models for a set of formulae phi, then I can think of this phi as essentially defining an axiom system for all those models. Yeah. Which actually is close to what happens in the way we describe most mathematical theories. Yeah. So, here let us take this, this is actually an elementary subset of piano arithmetic. Basically you have this set of natural numbers generated from 0 by a successor operation. So, here is our sigma, here is our sigma, here is our signature sigma, and then so in addition to these two operations there are these two relations, one is the equality relation and the other is a less than relation. So, for example, so this is in some sense elementary form of piano arithmetic, but we will look at piano arithmetic in greater detail later, the full axiom system. So, the notion of first order number theory as a first order theory of piano arithmetic is something we will look at later. Yeah. So, let us take this sigma structure and let us take the natural numbers under these operations and these relations, then you have these various formulae, right. Here is this formula which says that essentially 0 is not the successor of any element. Okay. I mean this. So, this first formula phi 1 should essentially be read as the successor of x cannot be equal to 0, and of course, we are x is a free variable here, remember that. Yeah, but so this is a so we will just keep that in mind. We will come to that what to do with free variables later. So, this essentially says if I have a pattern like successor of anything, it does not matter, then that value cannot be equal to 0, right. Okay. Here we have that here we have one of Peano's axioms actually. If the successor of x is equal to the successor of y, then x must be equal to y, right. Here is a trivial statement. For every x, there is a y which is its successor. Okay. You can sharpen this statement, make it more accurate, like saying that there exists a unique y, but unique y essentially means I will be adding another conjunct which says for all z such that z is equal to plus 1 of x, y is equal to z. I mean that is how one would define uniqueness, right. But anyway, this is a simple example of a model, and here is something which says that okay, if x is not 0, then it must be the successor of some y. Yeah. So, these are the formulations of this. So, what is now intuitively clear, though at the moment we do not have a proof system. So, we cannot actually prove it, but what is intuitively clear is that this structure n satisfies these 4 formulae phi 1 to phi 4. Yeah. So, n is therefore a model of these formulae. Notice that some of these formulae have free variables, some of these formulae do not have free variables. So, phi 3 and phi 4 do not have any free variables, right. So, they are universally quantified, whereas phi 1 and phi 2 have free variables, and yet somehow the truth of phi 1 and phi 2 is independent of those free variables, is independent of any valuation for those free variables. That is important to realize. In fact, that is the key to what most mathematics texts do. They do not actually explicitly give you put a quantifier anywhere in their axioms. They just state the axioms with free variables, and it is assumed that they are universally quantified, and that is something that needs to be justified. Yeah. Okay, and that can be very easily justified, but let us look at some other examples. So, here is the set of integers again with 0 and addition. Yeah. So, you have so I just so I can actually take any set of operations and any set of relations that I am interested in and form a structure, provided I have defined the carrier set in some way. So, this z I have taken the set of all integers, and I am interested especially in 0 and addition, and this equality is something that keeps on coming, it will keep on coming up. So, that is often a very basic binary predicate that we have to use. In fact, what we will very soon see is that what we require really is not just a first order logic, but a first order logic with equality as a basic predicate, which should always be there. Essentially what the reason for that becomes clear, because in any algebraic system equality is a basic predicate, and without equality it is very difficult to do any kind of manipulation. For example, two different syntactical expressions are not really equal syntactically, but it is quite possible that they are equal in terms of values when you think of the under all valuations, for example, in which case the notion of equality is something that is far more basic, and we will require that. But before we get on to first order logic with equality, let us first look at this. So, I have essentially these are some group axioms. Yeah. So, phi associativity basically just says for all x, y and z. I think I said somewhere that this is a short form for all x, for all y, for all z, and I will use a single pair of brackets so that I do not clutter up the notation with too many brackets. Yeah. Okay. So, then this is just the associativity law. Now, here in this particular case I have of course universally quantified it on all the free variable, on all the variables that I use in the body. The identity it should be more correctly called the right identity, but let us call it the identity. For all x, x plus 0 equals x, and then there is a right inverse. Yeah, for all x there exists a y such that x plus y equals 0. I mean, so y is the right, y is a right inverse of x, a right inverse of x. I mean, that is important. So, this does not say anything about uniqueness and so on and so forth. So, if you take this set of integers under 0 and plus, it is a structure that is a model, it is a model of these three axioms. So, that is essentially so that is an example. Now, of course, when you are talking about group theory itself, you might not be interested in the particular structures, but you might be interested in general properties of groups, right. So, for example, okay, here is another example where I add a new axiom called the commutative axiom, which says that for all x and y, x plus y equals y plus x, right. So, now if you look at phi prime, so phi let us say contained all these three formulae, and phi prime contains everything in phi and also the commutativity, then what you are saying is that this phi prime has as models only all commutative groups, all abelian groups, okay, and there the non-abelian groups are excluded from it, whereas phi includes both commutative and non-commutative groups and as models. Yeah. And of course, we have this notion of logical consequence as we did before. A sigma formula of psi is a logical consequence of a set phi of sigma formulae denoted phi proves psi, psi is a logical consequence of phi if and only if every model A of phi is also a model of psi. So, now the notion of logical consequence has been imported straight from propositional logic, as you can see, right. So, one question is that we had this notion of right inverses and without worrying about an individual model of these axioms, I might want to show, I might want to prove theorems that are true for all models of these axioms, right. That's the way we work polymorphically in most of mathematics and computer science. And so, one possible logical consequence that you might want to prove is that every there are left inverses also. Okay, so, this formula phi left inverse essentially says that every element x has a left inverse y. So, that y plus x is 0, right. And the fact that it is a left inverse, that there is such a left inverse usually can is proven in any mathematics text by assuming let x be some element, then by the axiom, the right inverse axiom, we get that there is a y such that x plus y is 0. And again, given that there is a y, again by the right inverse axiom, you know that there is some z. I mean, you cannot assume that x is you only know about right inverses. Okay. So you have to, so y must be having a right inverse. I do not know what it is, but it is some z, right. So, with these assumptions essentially what you can show is that y plus x gives you 0, and in all these cases what we have used are only these the group axioms or these two which have been marked 10 and 11 throughout this. So, essentially, so y plus x is 0. So, what you are essentially saying is that y is a left inverse of x. Okay, right. So, your left inverse formula actually is sort of proved by this proof, right. But this proof actually is fairly general in the sense that I can claim that every right inverse is also a left inverse, right, and the proof for that is so you take the formula left right inverse, which essentially says that every right inverse is also a left inverse. That is the formula for all x y. If x plus y is 0, then y plus x is 0, right. So, this can also be use the same proof, except that this part in red has to be replaced by something like, let x and y be elements such that x plus y equals 0, right. Then by since there is a right inverse for every element, there is some z such that y plus z equals 0, and then this whole proof goes through and essentially shows that y is the left inverse of x, right. So, this is how standard proofs go in mathematics, and often what happens is that essentially the same proofs can hold for sharper statements. In a certain sense, this is a sharper statement than the statement that just says that there exist left inverses, right. Here it says that every right inverse is also a left inverse, and given that every element has a right inverse, you know how to find the left inverse, because the same element is also a left inverse, right. So, it is in a certain sense a sharper statement, and this is also a logical consequence of the group axiom. So, this is like a typical proof, right. So, what we are really looking at is formalizing the notions of these proofs, of such proofs within first order logic. Okay. So, then there is this question of validity, which approximately is like tautologousness in propositional logic, but not quite. Okay. A validity is a slightly more general notion. So, let's take A to be some sigma structure and phi is some sigma formula. Then we will say that phi is valid in A if and only if A is a model of phi. Okay. So, that is one thing. So, validity comes directly from the notion of a model. Phi is valid. Now, this is where something close to being a tautology comes in. Phi is valid if and only if every sigma structure is a model of phi. Okay. Here, the reason it goes beyond the notion of tautologousness is because this phi could have free variables in it, for one thing. Secondly, all our language is parameterized on this signature sigma. So, you are always talking about validity only in the context of a certain sigma. It is not. So, in that sense, it is the parameter sigma is always present, right. So, we would say, so the notion of validity, and we will, okay. So, actually it should be denoted this way, but most books in logic do not distinguish between this symbol and this symbol. Okay. But I have tried to distinguish it because in one case you are talking about models, truth in models, in another case you are talking about logical consequence from a set of formulae, right. So, So, because of the fact that, so notice that if every sigma structure is a model of phi, then what you are essentially saying is that phi is also a logical consequence of the empty set of predicates. In that sense, this is the same as this, and because validity has the same notion, so if so anyway you are parameterized on a signature sigma, and you are saying for every sigma structure phi is, every sigma structure is a model of phi, which means that phi is true of every sigma structure regardless of valuations. So, in a certain sense it is a logical consequence of no assumptions. So, it is true for all sigma structures without any assumptions and without and independent of valuation. So, it is actually a logical consequence of an empty set of assumptions, right. So, most books would actually use this symbol for validity. They would also use this for models, though the types on the left hand sides are different. In the case of logical consequence, you are talking of the left hand side consisting of a set of formulae as assumptions, whereas in the case of models they are some other structures. I mean, there is a color difference, right, between green and brown. I mean, that is the difference. Yeah. So, but however, so you have to watch out for that confusion, but once you realize that they are using the same, they are overloading the same symbol for two different concepts, and they are overloading the same symbol for two different concepts precisely for this reason, because the notion of validity in the two cases will coincide. Therefore, you should not get confused by it. Okay. So, now what holds for a single formula is extended to sets of formulae. So, we will say that capital phi, which is a set of formulae, is valid in A if and only if A is a model of all the formulae in phi. So, for example, all groups are models of the group axioms, which we have seen before, right, and all abelian groups are models of the group axioms, including the commutativity axiom. So, in that sense, all these statements of commutativity, associativity, right inverse and identity are true in all those, in all structures with that signature, right. So, they are valid in all structures with that signature, and hence they are valid essentially in all groups, right. So, the set phi is valid if and only if every sigma structure is a model of phi, yeah, and this is the closest we come to having a set of tautologies. Okay. So, this portion corresponds to phi, this lowercase phi being a tautology. So, in particular, if phi has the form, has the shape of a propositional tautology, right. So, for example, if phi has, even though it might have free variables, if phi has the same shape as a propositional tautology, and by the same shape I mean, let us say it is of the form some psi or not psi. Okay. So, this is a certain now I am not really interested in what psi is. I am not interested in whether psi is got free variables or not. All I am saying is that the shape of this formula viewed as a tree, for example, is essentially like this, right. where psi itself might be some tree, all formulas of this shape are propositional tautologies, and in first order logic they will all be valid too, because you take the only restriction is that you have to somehow reconcile the terms, since it might have free variables, it might have terms, you have to reconcile the terms with some signature sigma, but except for that all these formulae will also be valid regardless of whether they have free variables or not, right. So, validity extends propositional tautology to signatures, arbitrary signatures. Yeah. So, now once you have validity, of course, you can also talk about logical equivalence. We will say that phi is logically equivalent to psi, and we will use the same notation, phi is equivalent to psi if this phi biconditional psi is valid for all sigma sigma structures. Yeah. Okay. So, the importance of studying propositional logic is essentially that now you can take all propositional tautologies. So, you take any propositional tautology like this, and what you can think of and you can think of this as essentially defining skeletons into which you can plug in first order logic formulae appropriately, right. So, if you take something with more than one, like let us say if you take a tautology like this, if you take, then basically what we are saying is for capital P and capital Q, you can substitute it by uniformly by any first order logic formulae, phi and psi maybe, and what you will still get is a tautology. So, tautologousness in propositional logic will be preserved as validity in first order logic, right. So, the only constraint is that the internal terms inside those phi and psi should conform to the signature given, that is it. Except for that, there are no other logical reasons. Yeah. So, that is why, so now we can import basically all propositional tautologies as skeletal structures onto which first order logic formulae may be hung uniformly. Yeah. Okay, so we will take the appropriate slashed versions as the negations of these semantical concepts, basically invalid or not equivalent and so on and so forth. Yeah. Right. Okay, now I have got a lot of exercises for you to do, of which there is this 4. Can you see this 4th one? So, this 4 essentially says that you take any formula phi, this is valid if and only if its universal closure is valid. Yeah. What is the universal closure of phi? You take all the free variables of phi and you put a universal quantifier for all of them, so that this one has no free variables left. Okay. And this essentially the fact that validity of phi is independent of its free variables means that if you universally close it, also that it remains valid. So, validity is preserved under universal closure, okay, which is why which is a good justification for why your mathematics books do not put these quantifiers before the axioms, and they just state the axioms with free variables, but they are essentially saying that they are considering only all those structures in which these axioms are valid. So, they are valid with free variables if and only if their universally quantified versions are also valid, and so, and therefore, it is perfectly consistent. right. Okay. And of course, the same thing also holds for sets of formulae, which is in, I should have probably put this. Okay. Okay, I should have changed the order of these two, but anyway. And the other question 3 essentially identifies these two concepts, right. So you can, but you can prove all this from an underlying semantical model. The other important things that you have to prove is that the existential and universal quantifiers are duals of each other. Okay. So, they satisfy an they satisfy an extended De Morgan's law, okay, which essentially means that not of for all x phi is logically equivalent to there exists x not of phi, and similarly not of there exists x phi is logically equivalent to for all x not of phi. Okay. So, one way of, so this is essentially like, so in a certain this universal quantifier is really like and extended to a possibly infinite number of indices, right. Similarly, this is essentially like OR extended possibly to an infinite number of indices. So, the fact that AND is commutative and associative allows you to define a big AND in propositional logic, but you can take a big AND of various propositions only for a finite set. So, this has to be a finite set. Okay. What for all allows you to do is that when your models are infinite sets like integers or rationals or reals, then what this allows you to do is it essentially allows you to state an infinitary conjunction in a finite sentence. Okay. So you can think of the quantifiers intuitively as dealing with a finitary representation for an infinitary conjunction or infinitary disjunction. Yeah. And so, it is so one obvious thing, supposing you have a sentence, a universally or an existentially quantified sentence for which has only finitary models. Okay. Then everything in that finitary model, so every first order logic sentence can be translated into an appropriate propositional sentence there with, except for the occurrence of free variables, right. So, every closed first order logic formula can be expressed in terms of a purely propositional logic formula. So, one thing is you could think of one simple example you could think of is supposing I take the theory of Booleans. It is a finitary model which just it is a carrier set with two values. So, take this itself as your sigma, right. I mean, so where is that? So, we had something, we had the entire algebra specified somewhere, right. Oh, that was in the notion of truth. Okay. Here is the signature, right. So, you take this signature of Booleans which is just a 2 element carrier set, all expressions in this can be evaluated and they will evaluate only to do this to one of these two values, right. You take a first order logic of Boolean algebra. I mean, after all, our signatures are arbitrary, there is absolutely no reason why we cannot define a first order logic of Boolean algebra. So, if you take a first order logic of Boolean algebra, what you can actually do is you can take all universally quantified sentences in the first order logic of Boolean algebra and translate them into purely propositional sentences by replacing all the variables by the values for 0 and 1, they whatever are your violet versions of 0 and 1, right, because those are the terms. It has two constants 0 and 1, right. So, there will be a violet 0 and a violet 1, and you replace it and you have purely propositional statements describing Boolean algebra, right. So, for finite models, all your universally quantified formulae and your existentially quantified formulae will reduce to pure propositional formulae with variables being replaced by all the possible values from that carrier set, that is it, right. And so you can think of, therefore, one thing. So, the idea of parameterizing propositions to get predicates is to allow for the fact that we want finitary representation of sentences for formulae or facts which might be infinitary in nature, right. And so at the level, when you are dealing with only finite models, at least theoretically it is not necessary to do first order logic, it is sufficient to just use propositional logic itself. Yeah. Okay. So, that is a piece of insight which most books do not give you actually. Then let's proceed further. Okay. So, there is logical validity and here is semantical concepts, right. Now, what is the okay. So, of course, all our concepts so far were parameterized on a signature, that signature was important. And now, the question is how do you deal with different kinds of signatures which might have some relationships among them, right. So, we had this notion of an expansion and a reduct somewhere, right. So, supposing one signature is contained in another. So, we took for example, the signature of integers or natural numbers with just 0 and successor. It is quite possible to expand that signature to include addition, multiplication. Actually, the moment you want to do first order number theory, you would require addition and multiplication, because the interesting questions like divisibility and primality and so on rely on addition and multiplication and maybe subtraction and division. Okay. So, at least addition and multiplication would be there. So, then what you would do is you would want to expand that signature sigma to a larger signature, let us say sigma prime, or in this case let us say sigma 1 and sigma 2, right. So, if you expand the signature sigma 1 to a signature sigma 2, and for any set phi of sigma 1 formulae, phi is satisfiable with respect to sigma 1 if and only if phi is satisfiable with respect to sigma 2. So, okay, I mean the important thing here, what you are saying is, by expanding the signature, all the interesting facts that I had previously with the smaller signature continue to hold in the expanded signature. Notice that phi 1, this set phi consists of sigma 1 formulae. So, that means it does not contain any of the operators in sigma 2 which are not there in sigma 1. Okay. So, the notion of satisfiability essentially means that you do not, so satisfiability is preserved under expansion of the signature, right. And so, you can just take the interpretations of common symbols according to sigma 1, and then for sigma 2 minus sigma 1 you can take any interpretation, any arbitrary interpretation, it does not matter, and then you can prove that satisfiability is preserved. Yeah. So, we can expand signatures like that. The other thing is distinguishability. Yeah. So, let us we can use first order logic formulae as a method of distinguishing two models, two models with the same signature, right. So, let us take let us not have any operations, let us just have the equality relation and the less than relation. Yeah. So there and so take the integers under equality and less than, take the rationals under equality and less than, right. So there is a formula, there is a first order logic way of expressing that the set of rationals is dense. Yeah. What does it mean? Between any two distinct rational numbers there exists another rational number, right. You take this, so this is expressed just this way for all x and z. If x is less than z, then there exists a y such that x is less than y and y is less than z. So that is the density, that's a density axiom, let us say, or a density formula. And it is clear that in the case of the integers this is not valid. Okay. So, in a certain sense this sentence, this is a sentence because it is universally quantified, it has no free variables, right. This sentence is a distinguishing formula between these two possible models, the rational numbers under equality and less than and the integers under equality and less than. On the other hand, this cannot be a distinguishing formula between the rationals and the reals, because both of them are dense, for example. So, in the case of rationals and reals, in order to distinguish between rationals and reals, you will require some other kind of formula, which and that formula is more complicated, because the reals are actually limits of infinite sets of rationals. So to formulate that in first order logic will take some effort, yeah, but let us not get into it. But basically you can think of witness formulae which can distinguish between two possible models having the same signature, right. Okay. So Q, so phi density is valid in Q, whereas it is not valid in, yeah, whereas it is not valid in Z, yeah. So I will stop here maybe.